So now let's move to two-port non-linearity. So this two-port non-linear device can be three-terminal or three-terminal or four-terminal. So here in this course we'll limit our analysis to three-terminal two-port devices. Okay. So if you have, again we have done this two-port non-linear passive, and if it is three-terminal, remember two-port three-terminal, it looks something like this, which is the common terminal. That is port 1 and port 2. Okay, and we'll analyze this particular two-port element in the same way as we did for a one-port or two-terminal element like a diode. Okay, so if you have some kind of VDC, or rather let me call this V1 and some kind of V2 here. Okay, and this current, let's say I2, and this current, let's say I1, if this is the case. Okay, then you can say that my I1 is some nonlinear function f1 of v1 comma v2. Okay, you can say like this, because this I1 will be a function of v1 and v2, and it could be some nonlinear function, and similarly I2 can also be another nonlinear function f2 of the same v1 comma v2. Okay, this much we can define, because this is nonlinear. Each of the currents at the ports can be defined by its own nonlinear function, and that nonlinear function will have independent variables v1 and v2. That is what it means. Okay, now if I increase this port 1 voltage by delta v1 and port 2 voltage by delta v2, then I definitely can say this I1 will be increased by delta I1, this I2 will be increased by delta I2, right? So if I increase V1 by delta V1 and V2 by delta V2, then I1 will be increased by delta I1, similarly delta V1, and if I increase this delta V2, I2 will be increased by delta I2, right? And this will be my total current. Okay, so again now you have a DC current plus its increment, which is a function of a voltage plus an increment. Initially you had only one voltage, and first when you are analyzing a two terminal element like diode, now you have two voltages because it's two port, and things are straightforward. Now you have to do the Taylor series expansion in two variables. So Taylor series expansion in two variables, if you do, it's the same thing. Let me do it only for this one, and the other one will simply follow. I1 delta I1 is equal to this. If you expand this function, nonlinear function and Taylor series, first you have value at that operating point, which is f1 of v1 comma v2 itself. Okay, which is the operating point. Okay, plus dou f1 by dou v1 at the operating point multiplied by delta v1 plus dou f1 by dou v2 multiplied by delta v2 is at the operating point. Operating point is v1 and v2. Okay, you take a derivative of the function 1 with respect to v1 and substitute at operating point value, and derivative of the function v2 and substitute it with the operating point value, and multiply it with delta v1 and delta v2 here. So similarly I2 plus delta I2 also follows as f2 comma v1 comma v2 plus dou f2 by dou v2, dou v1 at the operating point delta v1 plus dou f2 by dou v2 at the operating point multiplied by delta v2. Okay, now as I said, this is exactly same as this one. That is what we have written here. Initially we had written that here, and this is exactly same as this one. Then delta I1 will be this whole thing, and delta I2 will be this whole thing, right? So what does it mean? Delta I1, this function by, this function divided by delta v1, or derivative of this function by delta v1, I know this is going to be a constant, right? Because you take a slope of any non-linear function and you substitute or find the slope at that particular operating point, it is going to be a constant. You take, say this is my non-linear function, you take the slope of the function at any one point, it is going to be a constant. Okay, say for example the slope of this function itself, say this is some function and f dash of that function, it will be the derivative of this, right? If it is exponential, it is going to be again another exponential, right? Now what I am saying is, if I substitute at one operating point, then I will choose the slope of the function only at that particular point, this point. So this is going to be a constant always, right? So these values at that operating point is going to be a constant. So delta I is equal to some constant times delta V. So that constant is going to be a conductance, right? I is equal to conductance times V. Okay, and in your two-port nomenclature, you represent conductance by Y, right? So I1 can be represented as some Y11, okay, times delta V1 plus Y12, this 1 and 2, 1 and 1, 1 and 2 times delta V2, and delta I2 is equal to Y2 and 1 delta V1 plus Y22 delta V2. Okay, so it's very similar to that of a linear two-port that you had, right? So if you have, let me rewrite that particular expression here. Delta I1 is equal to Y11 delta V1 plus Y12 delta V2, okay, and delta I2 is equal to Y21 delta V1 plus Y22 delta V2. If you have that particular situation, then you can see, what I am indirectly saying is, if these, remember in the previous discussion you also had higher order terms, like you had in the single port or Taylor series expansion and single variable. So you will have delta V1 square, delta V2 square, and delta V1 cube and V2 cube and so on, like that. But we neglected the higher order terms, assuming this delta V1 and delta V2 are very small. Okay, so here also what we are saying is, if the increments delta V1, this increment delta V1 and delta V2 is very small compared to that of the V1 and V2, okay, then we can say that a two-port non-linear device can be linearized to a two-port linear network, and this is the expression of the two-port linear network. Okay, we derived it right from the fundamentals. Now how this two-port linear network will look, okay, that is what we have to do. So a two-port linear network defined by this expression should look something like this. First of all, this is delta I1. Okay, remember, if it was a single port or a two terminal, we said it will look like a resistor. But then if it is a two port, it doesn't look like a resistor anymore. It is like combination of Y11, Y12, Y21, Y22. These four parameters should appear accordingly. So I1 is y11 is defined by y11 times delta v1, meaning if this particular value of the voltage between this port 1 and then this common terminal, this is common, let us say ground, then this is say port 2, this is port 2, and then this will be delta I2 and this will be delta V2, right? This much we know. Now how do I define delta I1? Delta I1 will be y11 delta V1. This is delta V1. So if I put y11 here, okay, then some part of I1 will flow here, right? And so one contribution of I1 will be from y11 delta V1. Delta V1 is a voltage, multiplied by y11 will be my some part of delta I1. So next part will be y12 delta V2. Now remember, delta V2 is the voltage at the second port, but you want to define the first current with the voltage at the second port, so it should be done using a dependent current source. This dependent current source will be done y12 delta V2. Okay, similarly here I have delta V2 is appearing here, so this will be y22 and this will be a dependent current source to represent y21 delta V1, right? I hope this is clear. Okay, otherwise you go back and check the video, and then I hope this should be clear. Now this is the equivalent incremental representation of any two port 3 terminal. We have assumed 3 terminal, okay, that is why I am specifically mentioning 3 terminal. Any 2 port 3 terminal non-linear device, right? It's the incremental equivalent picture. But if I want it to act as an amplifier, see, finally my aim is to build an amplifier, okay, but will this work as an amplifier is a question. Okay, so if it has to work as an amplifier, what should we do?